All right, now we get to do I get to show you guys Thomson 8.4, which is the quark parton model. So in this chapter so far, right, we converted the Rosenbluth formula into this weird form structure function form factor. Unfortunately, I probably should have put this on the slides here. And then, right, we calculated what the scattering between the electron and the quark directly will look like, right? In fact, that's the formulas down here, right? Where if you're scattering off, the electron is scattering off the quark, right? You have these, you can write the differential cross section in terms of theta. So you get the differential cross section partial sigma by partial omega, which is going to be the angular dependence, right? We just wrapped up with reformulating it into what's known as the Lorentz invariant version of it, where instead of taking this derivative with respect to, d theta, d phi, right, you're taking this derivative in terms of q squared instead. Okay. All right. So what we're going to do is we're going to start with, we're going to put this pin this onto the wall somewhere, right? What we're going to do is we're going to think about, okay, so when the proton comes in, it does not carry all the momentum of the proton, right? Sorry, when the proton comes in, each of the quark, right? So imagine there's 4 things in this proton, right? Each of my fingertip actually carries, a fraction of the momentum as my hand goes from left to the right, right? So we can do the same thing with the proton, where let's say you have this little gray thing is the proton, right? Inside here, there's a quark, right? One of the quark, right? This is the proton, right? And this proton is going to carry a fraction of the energy and momentum, okay? How much of that? We're going to just quantify as right? So the 4 vector for the quark, so let's say, so this P2, right? Right, that's the entire proton, has some energy E2, and has some 3 momentum P2, okay? Right, so the momentum to carried by this one particular quark, we're going to quantify that as just some fraction of that, okay? And we're going to write this weird letter called XC, okay? It's spelled like this, okay? And usually I just squiggle a bunch of stuff and then it looks like that, okay? And we're going to have a fraction of this momentum, okay? And then since this is just a number, right, this will just turn out to be XC E2, comma, oops, forgot the XC, XC P2, right? And that's what this diagram is indicating, okay? So what's happening is that, right, you have an electron coming in, right? Oops, let's just draw this further through right here. Electron coming in, right, that has the momentum P1. It shoots off a photon, right, and therefore it goes out with a momentum P3. And that photon, instead of interacting with the entire proton, it actually just interacts with one of the quark inside the proton, okay? So it's very important for us to understand this little diagram really well, okay? Since this proton is carrying momentum P2, that one quark, right, is going to be carrying momentum XC times P2, okay? It's just a fraction of it, okay? And therefore, the outgoing quark that's the photon scatter off of will exit, right, with a momentum of XCP2 plus Q, right, because this is actually going this direction, okay? All right, so that's the whole setup, okay? So for the 4 momentum of the quark, right, so PQ, I guess you just use, instead of P2, just call PQ, right, it's XCP2, and then that's what I wrote up there, okay? And in all these cases, we're just going to use that the mass, the energy we're dealing with is much bigger than the mass of the quark, so we don't have to deal with the mass terms, okay? All right, so what does this mean? Okay, so this XC thing, right? This, don't worry, this, we're not going to carry this variable around too long, right? It's basically the momentum carried by one type of quark. Okay, I want to say type because just be careful. When we're scattering off these things, we actually cannot tell the difference between, oh, is it up quark number 1 or up quark number 2, because they are identical particles. Okay, so the form momentum of the outgoing scattered quark, right, is Sp2 plus Q, as we see up here. Okay, right, well, this quark still has mass of mq, right? Okay, so when you square any form momentum of a free particle by itself, right, you get the mass of that particle square. So therefore, Xcp2 square is going to be mq square, right? That's what that says. And since this particle is also treated as a free particle, just, that's being scattered off of Xcp2 plus Q, right? Also, well, when you square that form momentum, right, you also get mass of the Q. Okay, so why am I doing this? Okay, because what we can do is that we can rewrite Xcp2 plus Q square, right? Instead of, computing that as, well, MQ right away, we can expand this out, right? Just do a little FOIL thing, right? And then we can actually get Xc square P2 square. This turns out to be mass of the quark square, right? That's going to be equal to, well, the cross term is going to give you 2 times Xcp2 dot Q, and then you have the Q square back here also, right? Since this is the mass of the quark, this is the mass of the quark, they actually subtract each other. Therefore, we can find that, well, Q squared plus 2Xcp2 dot Q is actually equal to 0. Okay, what we can do is that, well, Xc, we can solve this equation for Xc, right? So we have Q squared equals to minus 2Xc P2 dot Q, right? And then solving this for Xc, we get that this is actually negative Q squared divided by 2P2 dot Q. Okay, and that's exactly what's written down here. Well, this looks familiar, especially if we make negative lowercase q squared into positive capital Q squared, right? This is actually exactly what we defined in section 8.1 as X, okay? Right? So this XC thing, right, that we just made up, the reason we picked XC is because it's an annoying letter to draw. So therefore, it's always a temporary thing. It actually turns out to be just X. So we actually don't have a new variable to have to deal with. It's the same old kinematic variable that we defined in 8.1. All right, okay. And this is also known as the Bjorken X, or, right, the momentum fraction of a particular type of quark, right? Or we can actually, in the future, we can talk about this in terms of the gluon fraction also. But, right, the fact that, this XC thing that we define, right, turns out to be X is really nice, because now we don't have to deal with another variable. Okay, what we're going to do now is going to go back to the result from the previous section, 8.3. Okay, remember that, right, the differential cross-section with respect to Q squared, right, can be written as this complicated equation, 2 pi alpha squared Q, the charge of the quark square divided by Q to the 4th, and then there's this long, fraction, the stuff in the bracket. Okay, what we can do is then we can reformulate this, right? This is, a electron scattering off a single quark, right? What we can do is that, well, instead of scattering off an entire quark, just an individual quark, right, we can reformulate this so that we're scattering off of a fraction of the momentum from a quark inside a proton. Okay, when you reformulate this, I'm going to skip a lot of the algebra steps that the book shows you. What happened is that basically this S here changed into SQ. Okay. What the heck is SQ? SQ right, is the Mandelstam variable for the fraction of the quark that's actually interacting with the electron, right? XCP2, right, plus, which is the quark, right? And P1 is the electron, right? Those two form momentum added together, and then you square it, gives you the Mandelstam variable S, okay? Right, if you, once again, you follow this out, right? So this is going to be XCP2 squared. So this is once again mass of the quark square, right? P1 squared is the form momentum of the electron squared, right? That's actually mass of the electron squared, right? Once again, we're going to go to the high energy limit where these masses are basically zero, okay? Or small relative to the energy we're dealing with, okay? And now we're left with, right, 2 times XC P2 dot P1, okay? And 2 times P2 dot P1 is actually exactly what equals to S, approximately equal to S in this high energy limit, okay? And therefore, right, this SQ is actually equal to XCS, right? And so remember, right, XC is actually equal to this old kinematic variable that we defined in 8.1 already, which is just X, okay? Right? So SQ is actually, oops, not that one up there. It's basically just a fraction of this S Mandelstam variable instead, okay? So, I mean, hopefully it makes sense, right? These Mandelstam variables is telling you kind of like how much energy is going into these collisions, right? If you're only having a fraction of the quark's energy going into collision, you're going to get a fraction of that, okay? And that fraction happens to be X, okay? Yeah. So that's what I'm saying in this bullet point here. Okay, so this formula, right, is the one that's the easiest to understand conceptually, right? Because, right, all we're doing is we did this whole calculations with quark electron scattering, right? We found this formula up here, right? And then what we change when we're dealing with, instead of scattering off a free quark, right? This quark is trapped inside a proton, and that quark carries a fraction of the momentum of the proton, right? The fraction actually happens to be X, right? Which is, when we define this XC thing, we didn't know it was going to turn into X, right? So, but it's going to be just X fraction of the momentum of the proton. And therefore, right, when we modify the result from 8.3, all we have to do is just change the center of mass of this particular collision. Sorry. All we have to do is change this Mandelstam variable. Instead of just being S, we just have a fraction of S, and therefore it's just X times S. Now what we're going to do is we're going to do a little bit more math gymnastic, just so we can see how we can measure these things in experiments. Okay, so 8.21 is very good to understand conceptually, but what we're going to do is, because we're going to try to disentangle the different quarks inside the proton in order for us to measure it. Okay, so going back to 8.1 again, okay, you can actually compute q square, right? Not just as negative q square, but also S minus the mass of the proton square, and then multiply that by the two kinematic variables x times y. Okay. Well, we can replace this q square, right? Sorry, capital Q square, right? By just putting a negative sign out here, right? And we're going to replace all of these x, right, as the fraction of the momentum carried by a particular quark, right? So instead of just x, you have xq. Instead of just y, you have yq, right? Instead of the mass of the proton, you have mass of the quark, right? Instead of the Mandelstam variable S, you have for the entire proton, you have it for the individual quark itself. Okay, since the mass of the quark is pretty small, you can just approximate that to be 0. Okay, so in this case, what you can do is you can rewrite this whole equation, right? Let's go over here, right? So q squared equals to negative sq xq yq, right? Solving this equation for q squared over sq, they're going to get minus x times q y times q yq. Okay, all right. I guess I skipped this little part in the book, but what happened is that xq times yq actually just equals to the y variable without the q. Okay, go back to this, because what happened is that the xq and the fraction of xq actually cancels out with the fraction inside the yq. All right. Okay, so right, with this q squared over sq, right, we can sub this back into here, right? This is actually equals to negative y, right? Okay, so we get, right, this the differential cross section, right, in terms of q squared. So be a little careful here, right? This y actually depends on q squared, right? Right, so it's not just independent variable. Okay, we're going to do this. We're going to do another switcher rule. We're going to make q squared, right? Convert this equation to depend on capital Q squared instead. When you do this little sign flip, right, what happens is that, well, the q to the fourth power doesn't do anything. And then what end up happening is that you can multiply out the stuff inside here, right? So because this is actually 1 plus 1 minus 2y plus y squared. Okay. This turns out to be a 2 here. You can factor out this 2, right? Combine this with the other 2 to get a factor of 4 outside. And then what you end up with is that you can have this differential cross section in terms of capital Q squared instead. And then you have this 1 minus y in parentheses. There's a reason why we put this in parentheses, plus y squared over 2. All right. Okay. So, right, this differential cross section, right, is explicitly depending on q squared and y, but it is also dependent on x also. Okay. Remember that y is equal to q squared over s minus mass of the proton squared times x. So we could, swap this in for something that depends on x also, but we're going to do this in terms of y because, right, we're going to see, right, is that we're going to see that this allows us to basically go back to, what section was that? When we were at in section 8.2, when we reformulated things in terms of x. Okay, so what's going to happen? What happened is that the book does about maybe half a page of algebra. Okay, so you can look at it if you can go through those algebra steps if you want. But what we want to do is we actually want to just kind of look at this equation that I'm going to prop down in here, 8.23, just to make sure it makes sense. Okay, so when you're scattering, when you have your proton coming in, right, this big circle is the proton, and then you have one particular quark coming in, okay, and then you have your electron, you have a photon exchange between them, right, and they go off in their new direction. Okay, so this is some quark, right? When this happens, right, you are not scatter unless you can tell which quark you actually scatter off of, right? All you'll measure is basically the outgoing angle here and whatever energy 3 here is, right? So you actually cannot tell difference between, whether I scatter off of quark number 1 or quark number 2 or quark number 3 and so on like that, right? So what you need to do is that you're going to have to, when you make these measurements experimentally where you can only measure theta and E3, right? You have to account for all the possible different quark that inside the proton you could scatter off of, okay? Right? You might be scattering off an up quark, you might be scattering off a down quark, we don't know, right? Because they both have electric charge, okay? So that's what this piece here is trying to show you, right? What we're going to do is we're going to compute a double differential cross section instead of just the differential equation in differential cross section in terms of q squared. We're going to have a second derivative added to it, which is the derivative with respect to x instead. Okay? Right? Right? And then, right, to account for the various different quarks constituents inside the proton, right, not only do you have this formula here, right, instead of this q squared here, this actually gets blown up into, right, basically the charge of the individual quarks. So this can be an up quark, down quark. We're actually going to have up bar, d bar in here also. The anti-quark also matters because they are actually created by a sea of gluon inside. They're called C quarks. Okay, so that's each of these different quarks. And then this Qi tells you what the charge of that individual quark is. Okay, and then this lowercase q, right, tells you basically the fraction of momentum exchange for that particular type of quark. Okay, so why are we doing this? Okay, we're going to erase some of this stuff so we can actually compare this to the next equation. Okay, what we're going to do is we're going to compare this to an equation that we derive in 8.2, which is this structure function stuff that, maybe when you saw it, saw the video previously, it's like, why are we doing this, right? So this is the reason why. Okay, notice that right here, I'm actually going to rewrite this even more explicitly. Okay, I'm going to multiply this into here. Okay, 1 minus y sum of qi square qi p, it's just a function of x, plus y squared over 2 sum of qi square qi of the proton because x, oops, sorry. Okay, now hopefully you see why we did this thing in section 8.2. Notice that, right? This thing is exactly what F2 over X is. This thing is exactly what F1 is. Okay, right? In fact, for electron-proton scattering, right, those are the exact same terms. Okay, that means we can see that, well, F2, right, is actually just X times the sum of all the quarks constituents squared, well, the Q squared of each of the quarks times the momentum of each of the parton, right, for that particular quark. Okay, so now we have a way to basically relate the cross section, right? Well, it's a double differential cross section, so you're going to have to make this measurement at different q square and at different x's. Okay, and then basically make a plot, and what you'll be able to do is you'll be able to figure out what fraction of the momentum is carried by each of the individual quark inside by measuring these structure functions. Okay, just a reminder, right? The F2 and F1 are actually related to each other by a factor of just 2x. Okay, so if we measure F2, we actually have F1 also. Okay, so for a proton, right, the charge component, the electric charge component, so there's also the strong charge, right, are the quarks. Okay, the anti-quarks also has to be accounted for, because what happened is that inside the proton, right, you have a gluon. What they'll do is they'll make quark anti-quark pairs. Okay, these are known as C quarks. Right, they annihilate, and then all of the stuff is happening inside the proton, on and off, and stuff like that. Okay. Okay. So the structure function is x times sum of all the different quark constituents. Okay. Okay. Right. So x, right. So for the up quark, right. So this is for the up quark. Well, the quark of an up, the charge of a up quark, right, is 2/3. So you square that, you get 2/3 squared, so it's just 4/9. Yeah. And then this Q, right, tells you how much, what fraction of the momentum that's being carried by that particular up quark. So this is the up quark parton. Sorry, I shouldn't have said. This is the up quark, right, fraction, momentum fraction that's being carried by the up quark itself. Okay. Similarly, right, you have the same thing for the down quark. So you have, well, 1/9. Okay. And then you have the anti version of that. But you know, the negative actually just squared away. So you actually get the positives here still. Okay. Just for me to make sure I think I said this previously. This is not the momentum transfer squared. This is the charge of the quark. Okay. Sorry about that. Okay. This is the momentum square. Sorry if I think I made that mistake previously. Okay. All right. Problem is that, well, the reason that, me making that mistake actually didn't matter, because the structure function cannot be calculated analytically. What do I mean by analytically? Meaning I can't just sit down on a piece of paper and then write the equation out, right? Because remember, this is telling you what fractions of the momentum are being carried with the different quarks inside, and also the C quarks and all these gluon making different quarks. Okay. So this is the strong interaction. So therefore it's non-perturbative, right? Remember, alpha strong is approximately 1. So therefore every term in the Feynman diagram actually matters, right? So therefore, you know, not only the tree level diagram, which is proportional to alpha s squared, matters, but, right, the 100th order diagram, right, which will be proportional to alpha squared to 200, that is still 1. So therefore, you actually have to account for this. So you actually have infinite number of diagrams you have to calculate, which is not possible to do. So we have to make these measurements experimentally. For the proton, okay, if you basically have if you actually have a collider, right? So collide an electron into a proton, okay, P1, P3, single theta, right? Right. You actually never measure this XCP2, right? Okay. What happened is that if you can do this at a particular Q square, right, and X, what you can do is you can make a plot of this structure function, right? Because this is proportional to d sigma dq square dx, right? So if you're holding these down here constant, then you can actually, this is actually proportional to the cross section. And since this is proportional to the cross section, it's proportional to the rate of the event that you're going to get out of it at that particular, at these particular x and q square. Okay. If you plot, you can take this measurement as a function of x, and the q square is going to be kept between 2 to 30. Okay. What happened is that you can actually find that it has this function like this. Okay. Let's just interpret what these data points, make sure this makes sense. Okay. right? So there's some peak here, right, at low x, okay? Okay. And this number actually, right, happens to be 0.18, okay? That's not, it's not the same as the 0.18 down here, but, right, what happened is that as you increase in x, right, so at low, let's not even quantify this like this, okay? At low x, right, you have a higher cross-section, right? And then as you increase x, you actually lose this cross-section, right? Remember, one thing is that, right, as you increase energy in the collision, it's less and less likely they would actually interact with each other, right? The cross-section goes down as the center mass energy of the scattering increases. So this decrease makes sense. This, I think, is probably just a turn-on effect. Actually, it's not that peak is actually real. But what happened? The way you use this plot is you basically compute the integral of this under the graph, right? Okay, when you compute this integral, okay, you get 0.18 as the answer, basically, right? So what this is telling you is that when you're shooting proton electrons into each other, right, 18% of the scattering, right, is due to this F2 piece of the interaction, okay, right? We're going to do the same gymnastic with the neutron, okay? We're going to go, the book goes through all the algebra, okay? But you do the same thing when you do this integral with the neutron, you get a different number, 0.12, okay? The reason for this different number is because, right, protons and neutrons have different amount of up and down quarks in them, okay? The reason this fraction is smaller for neutron is because, right, the fact that you have two down quarks instead of two up quarks, you have less electric charge inside the quark, inside the proton, okay? And I think I'm going to try to write a homework problem on this. What you can do is then using these two numbers and knowing that, right, there's two up quarks in the proton and two down quarks in the neutron, you can actually calculate what fraction of the momentum is being carried by the up quark during this collision, which is actually 0.36. And then the fraction of the constituents inside the proton for down quark is 0.18. Okay, so this is the reason why, right, we know that there's two up quarks and one down quark inside the proton. Okay, right, because this number is two times this big, right, of FD. Okay, right. And these numbers are measured to such high precision that we know that the constituents inside the proton is two up quarks and one down quark. Okay, and these are known as the valence quarks. Valence quarks meaning they exist in real life all the time. So no matter what's happening inside a proton, there's always going to be two up quarks and one down quark. There are these things also called C quarks that I mentioned. So if we go look at this diagram here, right, instead of interacting with the valence quark, okay, the electron can also interact with the C quark, okay? The C quarks are created, right, by gluons basically creating quarks and anti-quark pairs, and then you're only interacting with one of those, right, and then that scatters away, right? And this is where, right, you have very, very high energy. That's when you actually interact with the valence quark instead of the C. Sorry, when you interact with the C quarks instead of the valence quark. Okay, so by knowing this, you can actually disentangle whether or not you're interacting with the valence quark versus C quark, because if you're doing your scattering at some moderate Q square, meaning high enough energy so that you're actually probing inside the proton, right? You are actually interacting mostly with the valence quark. But if you push that Q square even higher, now you are going to be interacting with the C quarks, and you can actually disentangle the difference between the two. And that's what we're going to talk about in the next section to wrap up this chapter.